To understand why standard language models struggle with complex, ongoing tasks, we have to look at how they process data. Out of the box, an LLM is entirely stateless. It only knows its original training data and the exact text inside your current prompt. Because of this design, the model cannot retain any persistent memory between sessions. Furthermore, every model has a hard limit on how much text it can process at once, its context window. Once you hit that ceiling, the system simply drops information. Overcoming this structural limitation requires an architectural expansion known as Memory plus Retrieval-Augmented Generation, or Memory plus RAG. This framework surrounds the core LLM with a network of persistent databases and intelligent retrieval pipelines. Instead of relying solely on the prompt, the system queries these external stores and dynamically injects relevant facts and past interactions right before generating a response. Establishing this architecture is the first step toward context awareness. It provides the mechanical foundation required for a model to access information that exists outside its immediate prompt window or its static training weights. Human working memory maps to an AI buffer, long-term memory to persistent databases. Recall is vector retrieval, and reasoning is the LLM. Scaling up requires the advanced RAG architecture, L1 immediate buffers, L3 persistent databases, L4 semantic memory, and L5 external knowledge. Pushing high volumes of user queries through a flat system will cause rapid context degradation. To prevent critical failures at scale, developers must engineer this pipeline one exact layer at a time. Trying to shove all user history into a single monolithic database is a structural error. Robust memory demands this highly differentiated hierarchical design. We start building at the L1 layer, the conversation buffer. This handles the immediate back-and-forth context of a live session. A naive sliding window blindly appends the last few messages. Look at the left code. 5 short sentences and 5 massive paragraphs are treated exactly the same. Lengthy messages easily breach the context limit. Overflowing prompts trigger cascading failures, dropped inference speeds, skyrocketing costs, and truncated context. Fixing this requires mathematical advanced token-based systems, shown on the right. This logic calculates exact token volume. When it breaches the limit, it surgically trims the oldest data. This creates highly optimized, smaller prompts, faster inference times, better attention allocation by the model, and reduced hallucinated answers. Strict token trimming is not just an optimization, it is a mandatory safeguard required to protect the finite attention span of the LLM. With the L1 working memory stabilized, the system architecture scales outward to the L3 and L4 persistent memory layers. Short-term buffers are strictly temporary. During long, multi-day user sessions, data trimmed from the immediate context window is permanently lost if not stored elsewhere. To solve this, developers implement a vector database for L4 semantic memory. A specialized embedding model translates every user prompt into high-dimensional numerical vectors. When a new query enters, it maps into this exact mathematical coordinate space. Because similar concepts group numerically, semantic retrieval finds relevant memories based purely on underlying meaning. Integrating an embedding model with a vector database elevates the entire architecture. The AI possesses deep, persistent intelligence spanning the user's entire history. A common mistake is assuming a vector database alone solves all memory requirements. Pure semantic search has a massive blind spot, failing to retrieve exact keywords or numerical IDs. To patch this vulnerability, the system requires a hybrid retrieval architecture. To guarantee we don't miss specific terms, we add a keyword search stream running precisely in parallel with the vector search. Simultaneously, a metadata filtering stream isolates the search to specific users, preventing data bleeding between different accounts. The hybrid retriever takes outputs from all 3 streams, semantic concepts, exact matches, and filtered parameters, and aggregates them into one raw data pool. Before that data hits the LLM, it must pass through a cross-encoder re-ranking layer. This component mathematically scores mixed results, ensuring only the most highly relevant context moves forward. Standard out-of-the-box setups routinely hallucinate because they bypass this logic entirely. They lack the structural capability to cross-reference exact keyword hits with semantic intent. Let's apply this full theoretical pipeline to a highly practical scenario: A user inputs a new query into the system. What trading setup do I use? The L1 buffer retrieves recent stop-loss limits. The L3 database pulls a persistent fact. The user trades nifty options. L4 vector search matches the semantic momentum strategy, while keyword search catches the exact CE breakout. These 4 threads funnel directly into the RAG context builder. The context builder synthesizes the recent buffer, persistent account data, semantic strategy, and exact keyword hits into one highly organized prompt. That data is injected directly into the LLM alongside the user's original question. This millisecond orchestration of hierarchical data dictates the success of the model. By combining these exact layers, the AI generates a highly personalized, hallucination-free response grounded entirely in the user's actual history. This diagram illustrates the completed advanced RAG architecture. We have moved from a stateless model to a fully operational memory pipeline. A user query enters the system, passes through the token manager, queries the vector database, gets processed by the hybrid retriever and re-ranker, hits the context builder, and lands accurately at the LLM. It is a complete, unbroken data path. Notice the strict structural separation. Temporary conversational memory handles immediate bandwidth, while the persistent databases store long-term facts. Compare this rigorous engineering to the amateur practice of taking an unfiltered array of chat history and blindly injecting it into a language model. One scales cleanly, the other crashes under its own weight. Properly engineered memory architecture is your only structural defense against context degradation during complex production workloads. Deploying this successfully requires adhering to a strict engineering checklist. First, developers must implement strict mathematical token trimming at the buffer layer. Fixed message windows guarantee overflow and must be discarded. Second, retrieval systems must deploy a hybrid approach, combining exact keyword search with vector semantics and passing all data through dedicated re-rankers for relevance scoring. By correctly wiring these isolated components, the AI moves from processing isolated text strings to navigating a continuous, interconnected network of historical and semantic data. This combination of persistent memory and intelligent retrieval transforms a base LLM into a scalable, personalized system capable of retrieving and reasoning across